Every galaxy in existence is racing away from every other galaxy. The universe is stretching bigger every single second. But here's what breaks your brain. It's not expanding into anything. There is no edge, no border, no outside. We will visit the light that can never reach us, the force tearing reality apart faster each moment. And the reason this question makes no sense. If you're ready to have your mind bent, hit that like button and subscribe. Prepare yourselves. We begin. In 1929, an astronomer named Edwin Hubble pointed his telescope at distant galaxies and found something nobody expected. They were all moving, not just moving, fleeing. Every single galaxy beyond our local neighborhood was racing away from Earth, and the pattern made no sense. The farther away a galaxy was, the faster it retreated. A galaxy 200 million light-years away moved twice as fast as one only 100 million light-years distant. This was not random motion. This was a rule, a law written into the fabric of existence itself. Hubble measured this using something called redshift. When light travels from a moving source, its wavelength stretches or compresses depending on the direction. An ambulance siren drops in pitch as it speeds away because the sound waves stretch. Light does the same thing. If a galaxy moves toward you, its light shifts blue. If it moves away, the light shifts red. Hubble found that nearly every galaxy showed red-shifted light. They were all running from us. But here is what made it truly bizarre. These galaxies were not just moving through space, like cars on a highway. The space between us and them was growing. Think of it this way. If you stand on a spot and a friend walks away from you, they move through the room. But if the floor itself stretches, carrying you both apart while you stand still, that is different. That is what Hubble discovered. The universe itself was expanding. Before this, most scientists believed the cosmos was static, eternal, and unchanging. Albert Einstein himself initially rejected the idea of expansion because it seemed too strange. He even added a mathematical fudge factor to his equations to keep the universe still. When Hubble showed him the evidence, Einstein called it his biggest blunder. The data was undeniable. Galaxies were separating not because they exploded outward from some central point, but because reality itself was stretching. This discovery changed everything. If galaxies are moving apart now, they must have been closer together in the past. Keep rewinding time, and eventually, everything in the universe crunches down into a single point. That realization led to the most important theory in cosmology, the Big Bang. The universe had a beginning. It started small and has been growing ever since. But Hubble's finding raised a haunting question that we still wrestle with today. If the universe is expanding, what is it expanding into? The answer lies in understanding what expansion really means. Picture a rubber band with a wave drawn on it. Stretch the rubber band and watch what happens to the wave. The peaks spread farther apart. The wavelength increases. That stretched wave is redshift, and it proves something profound. Space itself is elastic. When astronomers look at distant galaxies, they analyze the light coming from them. Every element produces a unique fingerprint of colors. Hydrogen glows at specific wavelengths. So does helium, oxygen, and carbon. These patterns are like barcodes that never change. Except when we look at faraway galaxies, the barcodes shift. All the colors slide toward the red end of the spectrum. Not because the atoms changed, but because space stretched while the light traveled. The farther light travels, the more space expands during its journey. A photon leaving a galaxy 10 billion light years away spends 10 billion years crossing the cosmos. During that entire trip, every inch of space it passes through grows slightly larger. By the time it reaches our telescopes, its wavelength has stretched dramatically. Some galaxies are so distant, their light shifts beyond visible red into infrared, then microwaves. The most distant objects we detect emit light so stretched it becomes radio waves. This is confirmed science. We have measured it thousands of times. The redshift tells us exactly how much the universe expanded while that light traveled. A galaxy with a redshift of 1 has light stretched to double its original wavelength, meaning the universe doubled in size since that light was emitted. A redshift of 2 means the universe tripled in size. The math is precise, and the pattern holds across billions of observations. But redshift reveals something even stranger. Space does not expand everywhere equally. Inside galaxies, gravity holds things together. The distance between Earth and the nearby Andromeda galaxy is not growing, we are actually moving toward each other, pulled by mutual gravity. Expansion only dominates at vast scales, where gravity becomes too weak to resist it. On scales of hundreds of millions of light years and larger, space overpowers gravity and stretches everything apart. This creates a bizarre reality. You are not expanding. The space between atoms in your body stays constant. The space between planets in our solar system stays constant. Even the space between stars in our galaxy remains fixed. But the space between our galaxy and distant galaxy clusters grows every second. Right now, as you watch this, galaxies millions of light years away are getting farther from us, even though they sit perfectly still. What drives this stretching remains one of the deepest mysteries in physics. Before the universe was even a second old, something impossible happened. Space exploded. Not outward into some void, it exploded into more of itself. In less time than it takes light to cross the width of an atom, the entire cosmos, inflated by a factor so extreme that a region tinier than a proton swelled larger than a galaxy. This event, called cosmic inflation, happened so fast it makes nuclear explosions look frozen. Let me give you the numbers in a way that makes sense. Imagine a bacterium, microscopic, invisible without magnification. Now imagine that bacterium expanding to the size of the Milky Way galaxy in a billionth of a trillionth of a trillionth of a second. That is how fast inflation moved. The universe doubled in size every tiny fraction of time, doubling again and again, at least 80 times in rapid succession. By the time inflation ended, the cosmos had grown by a factor of at least 1026. That's a 1 followed by 26 zeros. This is confirmed theory, supported by multiple lines of evidence. Cosmic inflation solves problems that haunted cosmology for decades. Without it, the universe we observe should not exist. During inflation, space expanded faster than light. Wait, how can anything move faster than light? Einstein told us nothing can break that speed limit. Here is the key. Objects moving through space cannot exceed light speed, but space itself has no such restriction. Space can stretch as fast as it wants. The galaxies, carried along with expanding space, are not actually moving, they remain stationary while the distance between them grows. It is like standing on a moving walkway. You are not walking, but you are moving relative to someone standing off the walkway. Inflation was driven by something physicists call the inflaton field. This field filled all of space with enormous energy. That energy had a strange property. It created a repulsive gravitational force. Instead of pulling things together, it pushed space apart. The pressure was so intense that the universe exploded in size exponentially. Then, just as suddenly, the inflaton field decayed. Its energy transformed into particles. Matter and radiation flooded the cosmos. That transformation generated the incredible heat we call the Big Bang. Before inflation, the entire observable universe was packed into a space 100 billion times smaller than a proton. After inflation, it was nearly 3 feet across, and it had only been a tiny fraction of a second since the beginning. Everything we see today, every galaxy in every direction, all came from that impossibly small starting point. The implications are staggering. What caused inflation to start? What caused it to stop? And if it stopped here, did it stop everywhere? The question feels natural. If something expands, it must expand into something else. A balloon expands into the air around it. A city expands into surrounding land. Your lungs expand into your chest cavity. Everything we have ever seen that grows needs somewhere to grow into. So the universe must be expanding into some larger space, right? Wrong. Understanding why requires throwing away your deepest intuitions about space. The universe does not expand into anything because there is no outside. Space and the universe are the same thing. The universe is not an object sitting inside space, like a ball sitting inside a room. The universe is space itself, along with everything in it. When space expands, it is not pushing into some pre-existing void. It is simply becoming larger. More space comes into existence between galaxies, but that space is still part of the universe. Think of it this way. Imagine you are a two-dimensional creature living on the surface of a balloon. You can move forward, backward, left, and right, but you have no concept of up or down. The entire universe, for you, is the balloon's surface. Now the balloon inflates. From your perspective, everything moves farther apart. Other two-dimensional creatures you can see drift away from you. The surface area of your universe increases. But here is the critical point. The surface is not expanding into the air inside or outside the balloon. That third dimension does not exist for you. The surface just gets bigger, period. We are in a similar situation, but with 3 spatial dimensions instead of 2. Our universe is the entirety of space. When it expands, the volume of space increases, but it is not growing into some higher dimensional space that we can point to. There is no outside, because outside is a concept that only makes sense within space. The universe creates its own space as it goes. This is not speculation. This is a direct consequence of Einstein's general relativity, confirmed by over a century of observations. General relativity treats space and time as a unified four-dimensional fabric called space-time. This fabric can bend, twist, and stretch. The equations show that space-time itself is dynamic. It evolves. The geometry of the universe changes over time, causing distances between objects to increase or decrease. Asking what the universe expands into is like asking, what is north of the North Pole? The question assumes something exists beyond the boundary. But there is no boundary. The universe is all there is. By definition, everything that exists, every location, every moment in time, all of it is the universe. But if the universe includes everything, how can it be getting larger? That paradox leads us somewhere even stranger. Space is being manufactured right now. Not in some factory, not from raw materials. It is just appearing between distant galaxies. New cubic miles of vacuum materialize every moment. This sounds impossible. How can something come from nothing? Where does new space come from? The answer lies in what space actually is. We think of empty space as true nothingness, a void. But quantum physics tells us there is no such thing as empty space. Even in a perfect vacuum, far from any matter or radiation, space seethes with activity. Virtual particles pop into existence and vanish in less than a trillionth of a second. Fields permeate every point. Space itself carries energy. This energy, built into the fabric of space, drives expansion. Physicists call it vacuum energy or dark energy. It exerts negative pressure, which sounds like nonsense, until you realize pressure can push or pull. Positive pressure tries to compress things. Negative pressure does the opposite, it pulls things apart. The vacuum energy creates a repulsive gravitational force that stretches space. Here is the critical insight. When space expands, the vacuum energy density stays constant. Imagine a box, 1 cubic yard in volume, containing a fixed amount of energy. Now double the box's size to 2 cubic yards. Normal energy would spread out, the density would drop by half. But vacuum energy does not work that way. When the volume doubles, the total vacuum energy doubles too. The energy per cubic yard remains exactly the same. This means expansion is self-reinforcing. More space means more vacuum energy. More vacuum energy means faster expansion. Faster expansion creates even more space. The process feeds itself. Space manufactures more space indefinitely. The math behind this is general relativity. Einstein's field equations show how matter and energy curve space-time, but they also show how the curvature of space-time affects matter and energy. It's a feedback loop. When the dominant form of energy is vacuum energy, the solution to Einstein's equations is exponential expansion. The universe grows faster and faster. We see this acceleration happening. In the late 1990s, astronomers studied distant supernova explosions. These explosions have a known brightness, which lets us calculate their distance. The results shocked everyone. The expansion of the universe is not slowing down as gravity should demand. It is speeding up. Galaxies farther away separate from us at increasing rates. Something is pushing against gravity. and that something appears to be the energy of empty space itself. This discovery earned the Nobel Prize in Physics. It confirmed what Einstein's equations predicted, but what seemed too strange to believe. The vacuum has weight. Empty space pulls itself apart, and this process has no known limit. What happens when you combine infinite expansion with the fact that space itself has no edge? The question leads somewhere truly bizarre. Imagine two scenarios. In the first, galaxies fly through stationary space, like shrapnel from an explosion. In the second, galaxies sit motionless while the space between them grows. These sound similar, but they are fundamentally different, and only the second one matches reality. If galaxies were moving through space, Einstein's relativity would place strict limits on their speed. Nothing can move through space faster than light. Period. This is not a technology problem. It is a law of physics as absolute as they come. When astronomers measure galaxy velocities, many exceed light speed. Some galaxies separate from us at more than 3 times the speed of light. Under the explosion model, this would be impossible. But galaxies are not moving through space. They are being carried by space. The distinction matters enormously. A galaxy sitting still in space can nevertheless race away from us if the space between us expands fast enough. Think of ants on a stretching rubber band. The ants walk slowly across the band at normal ant speed. But while they walk, someone stretches the rubber. From the perspective of an ant at one end, an ant at the other end moves away much faster than any ant can walk. The stretching band carries it. This resolves the speed limit problem. Special relativity, which sets the light speed limit, only applies to objects moving through a fixed reference frame. It says nothing about space itself expanding. General relativity governs expanding space, and it allows space to stretch at any speed. When we say a galaxy moves away from us faster than light, we mean the distance between us grows faster than light would travel. Not that the galaxy moves through space faster than light. Here is another key difference. If galaxies flew through space from a central explosion, we should be able to find the center. We could trace all the motion vectors backward to see where they originated. But observations show something different. Every observer, no matter where they are in the universe, sees all distant galaxies moving away from them. There is no center, no special location where the explosion happened. The expansion looks the same from every vantage point. This only makes sense if space itself expands uniformly. Imagine baking bread with raisins mixed into the dough. As the bread rises, every raisin moves away from every other raisin. Pick any raisin, and it looks like all the others are fleeing from it. But no raisin is special. The dough between them simply grew. Our universe works the same way. Space is the dough. Galaxies are the raisins. The cosmic microwave background radiation gives us final proof. This ancient light fills the universe uniformly in all directions. If galaxies were moving through space, their motion would create patterns in this background. We should see a stronger signal in the direction of motion and a weaker signal behind. But the cosmic microwave background is almost perfectly smooth. The tiny variations we detect match expanding space, not moving galaxies. The universe is not a cloud of debris flying apart. It is space itself growing. The universe begins not at some location. Everywhere. All of space erupts into existence simultaneously. The time is 10 to 36 seconds after the beginning. That number is so small it defies comprehension. Write a decimal point, then 35 zeros, then a 1. That is how far we are from the first full second. At this moment, the entire observable universe fits into a region far smaller than a single proton. Every galaxy we see today, every star, every planet, all of it compressed into a space so tiny it makes atoms look like solar. The temperature exceeds 100 million trillion degrees. Matter as we know it cannot exist. Even atoms cannot form. Only pure energy fills this microscopic cosmos, vibrating at frequencies we cannot measure with any instrument. Then inflation begins. This is confirmed theory, supported by observations of the cosmic microwave background. Some form of energy floods the newborn universe. Physicists call it the inflated field, though we don't know exactly what it was. This energy dominates everything. It creates enormous pressure, but not the kind that compresses. Negative pressure, the kind that rips things apart. Space responds by doubling in size, then doubling again, and again, and again. In less time than light takes to cross the width of an atom, the universe doubles at least 80 times. Each doubling happens in about y-37 seconds. The math is staggering. 280 is a 1 with 24 zeros after it. The universe expands by at least that much in a time period so brief we have no way to directly observe it. During inflation, quantum fluctuations matter in ways they never do later. At such tiny scales, quantum mechanics dominates. Energy fluctuates randomly from point to point. Normally, these fluctuations are irrelevant, but inflation magnifies them. A tiny quantum ripple gets stretched across cosmic distances. Those ripples become the seeds for everything that forms later. Regions with slightly more energy density eventually collapse under their own gravity to form galaxies. Regions with less energy become the voids between galaxy clusters. We can still see these quantum fluctuations today. They appear as tiny temperature variations in the cosmic microwave background radiation. Satellites have mapped them across the entire sky. The pattern matches exactly what inflation predicts. Random quantum noise stretched to cosmic scale. Around 10 to 32 seconds after the beginning, inflation ends. The inflated field decays. Its enormous energy converts into particles. Quarks, electrons, photons flood into existence. The universe goes from nearly empty to extraordinarily dense in an instant. The temperature skyrockets even higher than before. This is what most people call the Big Bang, but it is actually the aftermath of inflation. The real bang was inflation itself. The universe continues expanding, but now much more slowly. Gravity begins to matter. Particles start to interact and cool. The cosmos evolves from pure energy toward matter and structure. All of this happens in less time than light takes to cross the distance between two atoms. And it sets up everything that comes after for the next 14 billion years. Take a proton, that particle at the center of every atom. It measures about 1 femtometer across 1 quadrillionth of a meter. Now divide that already and possibly tiny distance by 100 billion. What you get is the size of the observable universe before inflation. Everything we can see today started in a space smaller than the smallest thing we can measure. Every star in every galaxy, all the gas clouds, all the dark matter compressed into a volume that makes a proton look enormous. The density defies description. The laws of physics as we know them break down completely at such scales. Inflation took this microscopic seed and blew it up to massive proportions. By the time inflation ended, around 10 to 32 seconds after the beginning, the observable universe had grown to roughly 3 feet across. 3 feet. In less than a trillionth of a second, space expanded from subatomic to human scale. Then it kept expanding at a slower but still incredible rate. What makes this truly strange is that the entire universe might be infinite. The part we can observe, that 3-foot sphere after inflation, eventually grew into the 93 billion light-year sphere we see today. But it is just a tiny piece of the whole. The complete universe could extend forever in all directions. Inflation took an infinitesimal patch of that infinite space and stretched it enough that we can observe it. Think about what that means. Before inflation, regions of space now separated by billions of light years sat right next to each other. They were in contact. They could exchange energy and equalize their temperature. Then inflation ripped them apart faster than light could travel. Those regions can never communicate again. They are now separated by more space than light will ever cross. This solves a major problem in cosmology called the horizon problem. When we measure the cosmic microwave background radiation coming from opposite sides of the sky, we find it has exactly the same temperature to within 1 part in 100,000. Those regions are now 93 billion light years apart. Light traveling since the beginning of time could not have crossed that distance. So how did they reach the same temperature? Inflation provides the answer. Before inflation, all those distant regions were close together. They reached thermal equilibrium. Then inflation blew them apart so rapidly that they kept that same temperature. The uniformity we see today is a fossil record of a time when everything was touching. But here is the unsettling part. The same process that created our observable universe probably happened in countless other places. Each tiny quantum fluctuation in the early cosmos could have inflated into its own vast region. There might be infinite copies of observable universes, all from different microscopic seeds, all expanding through the same underlying space. Most of them would be forever beyond our view, separated by distances that grow faster than light can travel. We exist in one such bubble, a region that started smaller than an atom and inflated into everything we will ever see. And beyond our bubble lies something we can never reach. There is a wall around us, not made of matter, made of light. The cosmic microwave background forms a spherical shell enclosing the entire observable universe. It marks the farthest distance we can observe using light. Nothing beyond it can ever be seen, no matter how powerful our telescopes become. When the universe was 380,000 years old, something crucial happened. Before this moment, the cosmos was too hot for atoms to exist. Electrons zipped around freely, unattached to atomic nuclei. The universe was opaque. Light could not travel more than a short distance before hitting a free electron and scattering. Imagine trying to see through fog so thick you cannot make out your own hand. The early universe was like that, but with plasma instead of water vapor. Then the temperature dropped below 5,000 degrees. Suddenly, electrons could stick to protons and form hydrogen atoms. In a relatively brief period, all the free electrons combined with nuclei. The fog cleared. Light could finally travel freely. Photons that had been trapped, constantly scattering off electrons, were suddenly released. They have been traveling through space ever since. Those photons are what we detect as the cosmic microwave background. Every direction we look, we see this ancient light. It comes from a spherical shell surrounding us at a distance of 46 billion light years. That shell represents the moment the universe became transparent. Everything beyond that shell is hidden behind the cosmic fog of the earlier opaque era. The cosmic microwave background started as visible light at 5,000 degrees. It glowed orange like a hot ember. But over 14 billion years of travel, the expansion of space stretched its wavelength. Today, it arrives as microwave radiation with a temperature of just 3 degrees above absolute zero. The coldest natural phenomenon we can observe in space. Satellites detect it with sensitive instruments tuned to microwave frequencies. It is the oldest light in the universe, the afterglow of creation. And it is the ultimate proof that we live in a cosmos with no center and no edge, a universe that is all there is, and yet is forever growing larger. The cosmic microwave background, often abbreviated as the CMB, is the oldest photon bath that permeates the entire observable universe. It is the residual thermal energy from a time when the universe was a hot, dense, and opaque plasma of particles and radiation. This glow comes to us from an epoch known as the Epoch of Recombination, which occurred approximately 380,000 years after the Big Bang. Before this pivotal moment, the universe was so hot and dense that photons could not travel freely. They were constantly scattered by a thick fog of free electrons and protons. The universe was effectively a brilliant opaque fireball, with light and matter locked in a tight embrace. As the universe expanded and cooled, its temperature dropped below a critical threshold of about 3,000 Kelvin. At this point, electrons and protons were able to combine to form the first stable hydrogen atoms, a process called recombination. This sudden clearing of the cosmic fog allowed photons to travel across space, unimpeded for the first time. These photons, last scattered 13.8 billion years ago, have been traveling ever since, their wavelengths relentlessly stretched by the subsequent expansion of space. The discovery of this background radiation in 1965 by Arno Penzias and Robert Wilson at Bell Labs was a monumental, albeit accidental, achievement. They were troubleshooting a persistent, uniform microwave noise in their sensitive horn antenna, a noise that remained constant, regardless of where they pointed it or the time of day. After eliminating all potential terrestrial and instrumental sources, including famously cleaning out a pair of nesting pigeons and their droppings, the signal persisted. This persistent hiss was the whisper of creation itself, the cooled remnant of the hot Big Bang. This discovery provided the first direct, smoking gun evidence for the hot Big Bang theory, decisively defeating its rival, the steady-state theory. For this monumental discovery, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978. The CMB has a nearly perfect black-body spectrum, meaning its intensity at different wavelengths follows a precise curve dictated solely by its temperature. This was spectacularly confirmed by the Cosmic Background Explorer, COBE satellite in the early 1990s, which showed the CMB's spectrum matched a black body at 2.725 Kelvin with astonishing precision. This perfect black body curve is another powerful piece of evidence for a hot, dense origin of the universe. The COBE team, led by John Mather and George Smoot, also received Nobel Prizes for this work, which ushered in the era of precision cosmology. However, the most profound revelations came not from the perfection of the CMB, but from its tiny, crucial imperfections. When COBE's instruments were sensitive enough to map the sky, they discovered the CMB is not perfectly smooth. There are minuscule temperature variations, anisotropies, of about 1 part in 100,000, appearing as a mottled pattern of slightly warmer and slightly cooler spots across the entire celestial sphere. These tiny ripples, these millionth of a degree fluctuations, are the most important structures in the entire cosmos. They are the imprint of quantum mechanical fluctuations, the seeds of all cosmic structure. In the first infinitesimal fraction of a second after the Big Bang, the universe was thought to have undergone a period of hyper-expansion called inflation. During this inflationary epoch, the universe expanded by a factor of at least 1026 in a time span as short as y-32 seconds. This rapid expansion stretched microscopic quantum fluctuations inherent to the fabric of space-time itself to macroscopic scales. Regions that were randomly slightly denser due to these fluctuations possessed marginally stronger gravitational fields. These overdense regions acted as gravitational wells, attracting more matter towards them. The slightly cooler spots we see in the CMB correspond directly to these overdense regions. Why are they cooler? Because photons climbing out of these deeper gravitational wells lose energy, a phenomenon known as gravitational redshift. This process, predicted by Einstein's general theory of relativity, imprints the blueprint of the early universe's density field directly onto the temperature map of the CMB. Conversely, the warmer spots in the CMB correspond to underdense regions, from which photons did not have to lose as much energy to escape. Over the next 13.8 billion years, gravity acted relentlessly on these initial conditions. The overdense regions pulled in more and more dark matter and gas, growing denser and hotter until they collapsed to form the first stars, galaxies, and eventually the vast cosmic web of galaxy clusters and superclusters we see today. The underdense regions, starved of matter, evolved into the immense dark cosmic voids that separate these great structures. The CMB is therefore a cosmic palimpsest, a layered document where the earliest imprints of quantum mechanics are written in the language of gravity and thermodynamics. Furthermore, the specific statistical properties of these hot and cold spots serve as a powerful cosmological probe. By analyzing the apparent angular size of these ripples, physicists can perform a fundamental geometric test, on the fabric of space-time itself. The physical size of the largest ripples is determined by the distance a sound wave could travel through the primordial plasma before recombination, a scale known as the sound horizon. We know this intrinsic size from our models of the early universe. By measuring the angular size that this standard ruler subtends on our sky today, we can determine the geometry of the universe along the line of sight. If space were positively curved like the surface of a sphere, light rays would converge and make the ripples appear larger than they intrinsically are. If space were negatively curved like a saddle, light rays would diverge and make the ripples appear smaller. In a flat, Euclidean universe, the angular size would match the predictions based on the intrinsic size and the distance to the CMB. The data from multiple satellite missions, most precisely from the Planck satellite, is unequivocal. The universe is flat to within a margin of error of 0.2%. This observed flatness is a profound cosmological puzzle, one that finds its most compelling explanation in the theory of cosmic inflation. The CMB thus acts as a triple revelation. It confirms the hot Big Bang, it reveals the quantum seeds of structure, and it measures the flat geometry of the cosmos. 2. Boundaries and horizons, imprisoned in a sphere of light. The cosmic microwave background represents the ultimate wall of sight, the final scattering surface from which the oldest photons in the universe originate. It shows us the effective edge of the observable universe in time, a shimmering shell of light emitted 13.8 billion years ago. But this shell is profoundly misunderstood. It is not a physical boundary, not a membrane or a wall, but a horizon in space-time, the limit of how far we can see due to the finite age of the universe and the finite speed of light. Space itself, the three-dimensional fabric of reality, continues far beyond that shell, presumably filled with galaxies, stars, and planets. Just like the ones we see, there are undoubtedly galaxies out there whose light has not had sufficient time to travel the vast, expanding distance to reach us since the beginning of the universe. And due to the accelerating expansion driven by dark energy, that light never will. We are fundamentally causally disconnected from those regions. You, right now, reside at the center of a sphere, a cosmic bubble known as the observable universe. This sphere has a co-moving radius of approximately 46 billion light-years. Everything you can possibly observe, every galaxy, every quasar, every star, every photon that will ever reach your eyes or your telescopes, is contained within this sphere. This observable bubble is estimated to contain a staggering 2 trillion galaxies, each a colossal island of hundreds of billions of stars. Yet, for all its immensity, this bubble is almost certainly far smaller than the actual universe, which may be infinite in extent. A logical and frequently asked question arises. How can the observable universe be 46 billion light-years in radius if the universe is only 13.8 billion years old? Shouldn't the most distant objects we can see be only 13.8 billion light-years away? The resolution to this apparent paradox reveals the profound and non-intuitive nature of cosmic expansion. The key is to distinguish between the look-back time of an object and its proper distance today. When a photon that we detect today from a distant galaxy began its journey 13 billion years ago, The space between our location and that galaxy was much more compact. The universe was a fraction of its current size. During the photon's multi-billion-year voyage across the cosmos, the very fabric of space through which it traveled was itself stretching. The galaxy that emitted the photon was receding from us as space expanded, meaning the photon was not just traversing a static distance, it was chasing a moving target. It is analogous to a child running on a moving walkway that is itself being stretched. The total distance covered is much greater than the length of the walkway when the child started. By the time the photon finally arrives at our telescopes, the original galaxy is now located a staggering 46 billion light-years away. This defines the particle horizon, the ultimate limit based on the farthest distance from which light could have reached us since the Big Bang, accounting for the expansion of space. There is another, more philosophically troubling horizon, the cosmic event horizon. This is not a boundary of what we can see from the past, but a boundary of what we can ever know in the future. The cosmic event horizon marks the farthest co-moving distance from which a signal emitted today could ever possibly reach us in the infinite future. Due to the accelerating expansion of the universe driven by dark energy, galaxies beyond a certain distance are receding from us faster than the speed of light. This is not a violation of special relativity, which forbids objects from moving through space faster than light, but a consequence of space itself expanding, carrying galaxies along with it. Even if a galaxy beyond this horizon were to shine a laser beam directly at us at this very moment, that light would be trapped in an expanding space where the gap it must cross is widening faster than the beam. The photon would be like a swimmer trying to cross a river that is widening faster than they can swim. They would make progress, but the far shore would always recede faster. This creates a deeply strange and counterintuitive reality. We can currently see galaxies up to 46 billion light-years away because the light they emitted in the distant past, when the universe was smaller and they were closer, is only just arriving now. But for many of those same galaxies, if they were to emit light at this very moment, they are already beyond our cosmic event. We will forever see only their ancient past, a fading portrait from their youth. That image will not just remain static, it will slowly redden and dim as the expanding space stretches the photons to longer infrared wavelengths and reduces their flux until they are forever lost to the void. This concept of a personal horizon extends to every observer in the universe. Every person and every hypothetical alien civilization in a distant galaxy has their own unique observable sphere centered precisely on their own location. An alien living in a galaxy 10 billion light-years from Earth has a different observable universe than we do. Their bubble overlaps with ours partially, but they see galaxies that lie beyond our horizon, and we see galaxies that are forever hidden from them. There is no universal center, no privileged vantage point from which one can see the entire universe. We are each trapped within our own bubble of visibility, a private cosmos defined by our location in space-time. And in a profound and unsettling sense, these bubbles are shrinking. As the acceleration of the universe continues, more and more galaxies cross the cosmic event horizon every moment, vanishing forever from our potential future view. They are not moving away in a traditional sense. They are being carried beyond the point of no return by the stretching of space itself. The universe that astronomers will observe trillions of years from now will be immeasurably emptier and darker. The light from all galaxies outside our local group will have red-shifted into invisibility, and the night sky, though still filled with the faded CMB, will be devoid of external galaxies. Our cosmic island will have become a lonely archipelago in an ever-darkening sea. 3. The engine of the cosmos. Dark energy and accelerating expansion. Gravity, as described by Einstein's theory of general relativity, is the curvature of space-time by mass and energy. It is an attractive force, pulling mass together on all scales, from apples falling to Earth to galaxies orbiting within clusters. Given this universal attraction, the collective gravitational pull of all the matter in the universe should be acting as a brake on the cosmic expansion. The primary goal of cosmology in the late 20th century was to measure the precise rate of this deceleration. Two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out in the 1990s to measure the expansion history. They used Type Ia supernova as cosmic distance markers, or standard candles. These supernovae occur when a white dwarf star in a binary system accretes enough matter from its companion to exceed the Chandrasekhar limit, triggering a thermonuclear explosion. Because this critical mass is always the same, the intrinsic brightness of these explosions is remarkably uniform. By measuring how bright these standard candles appear from Earth, astronomers can calculate their distance with high precision. Simultaneously, by measuring the redshift of their host galaxy's light, they can determine how much the universe has expanded since the supernova exploded. The results, announced in 1998, were shocking and unanimously pointed to a conclusion that defied expectation. The distant supernovae were about 25% fainter than they should have been in a universe whose expansion was slowing down. This dimness meant they were farther away than predicted by any decelerating model. The inescapable conclusion was that the expansion of the universe is not slowing down due to gravity, it is accelerating. Galaxies are flying apart from each other faster now than they were billions of years ago. It was as if you threw a ball into the air, and instead of slowing down and falling back, it shot away from you at an ever-increasing speed. This discovery was so revolutionary and paradigm-shattering that it earned Saul Perlmutter, Brian P. Schmidt, and Adam G. Rees the Nobel Prize in Physics, and the cause of this acceleration was dubbed dark energy, a name that frankly admits our profound ignorance of its fundamental nature. Dark energy appears to be a property of space itself, a constant energy density that permeates the vacuum of empty space. This concept has a historical precedent in Einstein's cosmological constant, represented by the Greek letter lambda, which he originally introduced to achieve a static universe and later called his greatest blunder. In the context of modern cosmology, lambda represents the energy density of the vacuum. The critical property of dark energy is that its energy density remains constant as the universe expands. This is in stark contrast to matter and radiation, whose energy densities decrease as the universe grows larger and dilutes them. Think of a box containing a fixed number of particles, matter. As the box expands, the density of particles drops. Now imagine a box where the energy density is a fixed property of the box itself. As the box expands, the energy density remains the same, meaning the total energy increases. This is the bizarre behavior of dark energy. As the universe expands and creates more cubic light years of space, the total amount of dark energy increases. More dark energy creates stronger repulsive gravity, which drives faster expansion, which creates more space, which adds more dark energy. This creates a powerful, self-reinforcing feedback loop. Current precision measurements, combining data from the CMB supernova and baryon acoustic oscillations, indicate that dark energy constitutes about 68% of the total mass energy content of the universe. Dark matter, the invisible, non-luminous substance that provides the gravitational scaffolding for galaxies and clusters, makes up about 27%. The ordinary matter, composed of atoms, the stuff that makes up stars, planets, gas clouds, and us, comprises a mere 5% of the cosmos. We are but a minor contaminant in a universe dominated by dark and unknown components. We live at a unique cosmic moment, a transitional period in the 13.8 billion year history of the universe. For the first several billion years, the universe was dominated by matter and radiation, and the expansion was decelerating. Gravity was winning. But around 5 to 6 billion years ago, a cosmic crossover occurred. The universe had expanded enough that the density of matter dropped below the constant density of dark energy. From that point forward, repulsion won over attraction, and the expansion began to accelerate. We now live in the dark energy-dominated era. The ultimate fate of the universe hinges entirely on the nature of dark energy. If dark energy is indeed the simple cosmological constant, a constant vacuum energy, then the universe will expand forever in a scenario known as the heat death, or big freeze. The expansion will continue to accelerate. Galaxies beyond our local group will vanish from view. Star formation will eventually cease, and the universe will approach a state of maximum entropy, cold, dark, and dilute. If, however, dark energy is something more dynamic, a field that evolves over time, other fates are possible. In a particularly dramatic scenario, if the energy density of dark energy were to increase over time, it could lead to a big rip. In this model, dark energy's repulsive force would grow without bound. First, it would tear apart galaxy clusters, then individual galaxies, then solar systems. In the final moments, it would overcome the electromagnetic force holding atoms together, and even the strong force holding atomic nuclei together, ripping apart all structures in a catastrophic end. Whether the Big Rip is our future depends on the detailed physics of dark energy, which remains one of the greatest unsolved mysteries in all of science. 4. Beyond the known. Speculations on the nature of reality. What lies beyond our cosmic horizon? The honest, rigorous scientific answer is that we do not know, and we can never know through direct observation or experiment. The regions beyond the particle horizon are causally disconnected from us. No information, no signal, no influence of any kind can ever reach us. However, science is not limited to direct observation. It can use the power of reason and extrapolation to make educated guesses. The primary guiding principle is the Copernican principle, or the principle of mediocrity, which states that our position in the universe is not special or privileged. The laws of physics, as tested in our laboratories and observed in the most distant galaxies we can see, appear uniform and isotropic. Distant galaxies look fundamentally similar to nearby ones. obeying the same rules of gravity, nuclear physics, and electromagnetism. It is therefore a reasonable, albeit unprovable, inference that the universe beyond our horizon is broadly similar to the universe within it. It likely contains more galaxies, stars, and planets, organized into a vast cosmic web of filaments and voids, stretching on for distances that dwarf our observable bubble. But a more radical and thrilling possibility emerges from the leading theory of the very early universe: cosmic inflation. Inflation posits that the large-scale uniformity of the universe was established by a period of ultra-rapid expansion which smoothed out any initial irregularities. However, due to its quantum nature, inflation may not have ended everywhere at once. It could be eternal, with different regions of space-time stopping their inflation at different times, like bubbles forming in a boiling pot of water. Each of these bubble universes would be a separate, expanding cosmos, causally disconnected from the others. In this multiverse scenario, the fundamental constants of nature, the strength of gravity, the mass of electrons, the value of the cosmological constant, even the number of spatial dimensions could have different values in these distant domains. Our observable universe would be just one bubble in a vast multiverse, a cosmic froth of universes, each with its own unique physical laws. We exist in this particular bubble not because it is special, but simply because its constants are finely tuned to allow for the formation of atoms, stars, planets, and ultimately, life. This concept, while seemingly science-fictional, is a natural and robust prediction of many well-motivated models of eternal inflation. The observed geometry of space, as revealed by the CMB, also points to a profound possibility: infinity. The universe is measured to be geometrically flat to an extraordinary degree of precision. In the context of general relativity, a flat universe is consistent with, and often implies, an infinite spatial extent. If the universe is truly infinite, then the implications are staggering. It would contain an infinite number of galaxies, stars, and planets. In an infinite universe with a finite number of ways to arrange a finite number of types of particles in a finite volume, every possible configuration must occur, not just once, but an infinite number of times. This leads to the concept of Boltzmann brains and cosmic duplicates. Somewhere in the vastness beyond our horizon, there would exist a galaxy identical to the Milky Way, an identical Earth with an identical you reading an identical sentence. These are not mere look-alikes but exact physical duplicates, arising from the random but inevitable permutations in an infinite cosmos. Yet, due to the cosmic horizons, these duplicates are forever beyond our reach, making this mind-bending philosophical concept a potentially physical reality that is nonetheless unobservable. We are left to map our finite island with ever-increasing precision, using its properties to constrain the nature of the boundless and likely infinite ocean that surrounds it. Conclusion. Our unique and humble place in the cosmos. We are privileged to live at a cosmic crossroads, a brief golden era in the long-term history of the universe. It is a time when the universe is still transparent, filled with the light of stars and galaxies, and the afterglow of creation is still detectable. We can look back to the dawn of time through the CMB and use powerful telescopes to trace the evolution of cosmic structure over billions of years. Simultaneously, we have deduced the future trajectory of the cosmos, a future of accelerating expansion and increasing isolation. Our observable universe, for all its immensity containing 2 trillion galaxies, is but a finite island in an unimaginably larger cosmos. The walls of our bubble are not made of matter, but of the fundamental constants of physics, the finite speed of light and the relentless, mysterious expansion of space itself. Dark energy, this enigmatic force we barely understand, now holds the reins of cosmic destiny. It constitutes the majority of the universe's content and is steering it toward a future that is cold, dark, and lonely. The most profound lesson of modern cosmology is one of humility. We have used the tools of science to peer into the deepest depths of space and time, only to discover that the universe we can see and study is only a tiny, accessible fraction of a reality that is mostly and forever hidden from us. We have learned that the familiar world of atoms is a mere 5% contaminant in a sea of dark matter and dark energy. We have learned that our entire cosmic history, from quantum seeds to galactic empires, is confined to a bubble whose boundaries are shrinking in a meaningful way. We are left to map our island with exquisite detail, to gaze at its shores with wonder and curiosity, and to use the power of human reason to guess at the nature of the boundless, and perhaps infinite, ocean that lies beyond. The universe is under no obligation to make sense to us, yet through patient observation and brilliant deduction, we have managed to unravel a story more magnificent and strange than any myth. If dark energy's dominance had been delayed by a few billion years, the universe would have had more time for gravity to work its magic. Gravity, acting over a longer duration, could have pulled matter into even larger and more complex structures than we observe today. We might have witnessed superclusters of galaxies on scales that would dwarf the Sloan Great Wall or the Hercules Corona Borealis Great Wall. The cosmic web, the large-scale structure of the universe, could have been even more intricate, with denser filaments and more profound voids. More time before acceleration took over would have allowed for more generations of stars to be born, live and die, enriching the cosmos with heavy elements. The chemical diversity available for planet formation and potentially life could have been even greater. The timing of dark energy's emergence was not preordained. It was a consequence of the specific densities of matter and dark energy in our universe. This specific timing, this cosmic coincidence, has directly shaped the richness and scale of everything we can observe. It determined the maximum size of structures and the ultimate number of galaxies we can see. We are the products of a universe where the balance between attraction and repulsion tipped at a very specific moment. That moment allowed for us to exist and to see a universe filled with structure, but not so much structure that it collapsed in on itself. 68% of all existence is this mysterious, repulsive force actively pushing the fabric of reality apart. This dominant component of the cosmos is not matter, not radiation, but something that acts against the very force that builds galaxies. And despite it constituting the majority of everything, we still do not know what dark energy fundamentally is. Its nature remains the most profound enigma in modern physics. Point to the emptiest place you can imagine, perhaps a region in the boat's void, a vast spherical region of space largely empty of galaxies. Think of the deep, cold space between galaxy superclusters, far from the light of any star or the glow of any nebula. Imagine a perfect void, a cubic meter of space so isolated that it contains, on average, only a handful of hydrogen atoms. A space with no dust, no planets, no radiation from nearby stars, a region that appears to be perfect nothingness. That seemingly empty space, according to our best theories of physics, is not empty at all. It still contains a fundamental energy. This idea of energy inherent to space itself directly challenges our classical intuition about vacuums and nothingness. But quantum mechanics, the most successfully tested framework in all of physics, insists that this is true. In the framework of quantum field theory, the universe is not composed of isolated particles, but of fundamental fields that permeate all of space-time. The electromagnetic field exists everywhere, and its excitations are what we perceive as photons. Similarly, there is an electron field everywhere, and what we call an electron is a localized excitation of that field. Quarks have their fields, neutrinos have theirs, and even the Higgs boson is a manifestation of the all-pervading Higgs field. These quantum fields are not passive backgrounds. They are dynamic entities with properties and energy. They possess energy even in their lowest possible state, when they are not excited into what we would call a particle. The lowest energy state of a quantum field is what we call the vacuum state. Classically, you might assume this vacuum state has exactly zero energy, a true and perfect void. But quantum mechanics, through the Heisenberg uncertainty principle, explicitly forbids any field from having exactly zero energy. The uncertainty principle creates a fundamental fuzziness in nature, preventing both a field's value and its rate of change from being precisely zero simultaneously. This means the fields must constantly fluctuate, jittering around their 0 points even in their ground state. Energy and time are linked by uncertainty. Over incredibly brief time intervals, large amounts of energy can fluctuate into existence. These temporary borrowings of energy can manifest as virtual particle-antiparticle pairs that pop into and out of existence before they can be directly measured. These quantum fluctuations are not just mathematical artifacts, they have real, measurable physical effects. The Casimir effect demonstrates this vacuum energy directly and unequivocally. Take two perfectly smooth, uncharged, conductive metal plates and place them parallel to each other, separated by a microscopic gap in a perfect vacuum. Incredibly, the plates will experience a slight but measurable force pulling them together. The explanation lies in the nature of the quantum fluctuations in the space between the plates. Between the plates, only those virtual photons whose wavelengths fit perfectly into the gap can exist. Longer wavelengths are excluded. Outside the plates, virtual photons of all wavelengths can flash into existence. This creates an imbalance. There is a greater density of quantum fluctuations outside the plates than inside the gap. The greater external pressure literally pushes the plates together, a force that has been experimentally confirmed with high precision. Vacuum energy is, therefore, not mere theoretical speculation. It is a physically real phenomenon that exerts force. Now, if one were to theoretically add up the contributions of vacuum energy from all the quantum fields throughout the universe, the result is a number of catastrophic proportions. The naive calculation suggests the vacuum should contain so much energy that its gravitational repulsion would be immense. The universe would have inflated itself into oblivion within the first instant after the Big Bang. The expansion would have been so violent that no particles could have clung together, no atoms could have formed, let alone stars, galaxies, or planets. Clearly, since we are here to ponder the question, something is profoundly wrong with this straightforward calculation. The discrepancy between the theoretical prediction and the observed value of dark energy is not just large. It is the most embarrassing failure of quantitative prediction in the history of science. Theoretical predictions for the vacuum energy density exceed the observational measurements by 120 orders of magnitude. That is not a typo. It is a 1 followed by 120 zeros, a number so vast it defies any meaningful analogy. This monumental problem is known as the cosmological constant problem. Why is the vacuum energy so much smaller than quantum field theory predicts? Some physicists suggest that perhaps unknown cancellations occur between different fields. Maybe the positive energy contributions from some fields are almost perfectly offset by negative energy contributions from others. This would leave only a tiny, non-zero remainder that we observe as dark energy. However, no known mechanism in physics explains why this cancellation should be so exquisitely fine-tuned to 120 decimal places. Others propose that our understanding of quantum field theory breaks down at the very high energies relevant to the vacuum. Perhaps a theory of quantum gravity, which unites general relativity with quantum mechanics, will naturally resolve this problem. These ideas, while promising, remain entirely speculative and without experimental confirmation. What we know for certain is that vacuum energy exists, and it has the right properties to be dark energy. A constant vacuum energy density would remain constant as space expands, unlike matter, which dilutes. It would create a negative pressure, which in the equations of general relativity produces a repulsive gravitational effect. The observed acceleration of the universe's expansion matches precisely what a cosmological constant from vacuum energy would do. We just cannot explain why it has the specific, infinitesimally small value that it does. Empty space is not empty. It seethes with invisible quantum activity. Virtual particles flash in and out of existence in a relentless frothing sea of energy. Fields oscillate at their minimum energy, a constant hum of activity beneath the perception of our senses. This quantum frothing has weight. It carries an energy density that curves space-time according to Einstein's equations. And this curvature manifests not as attraction, but as a repulsion that pushes the universe apart. The vacuum is alive with an invisible energy that ultimately controls the fate of the entire cosmos. There are two fundamental walls that surround us, both invisible and absolute in their own ways. One wall, the particle horizon, marks the farthest distance from which light could have possibly traveled to us since the Big Bang. The other wall, the cosmic event horizon, marks the farthest distance from which light emitted today could ever reach us in the infinite future. They are not in the same place. They demarcate different and profound limits to our knowledge of the universe. And both of these horizons move and evolve over cosmic time, changing the very nature of our observable reality. The particle horizon currently sits at a moving distance of about 46 billion light-years from Earth. This boundary represents the absolute edge of our past light cone. It is the limit of the observable universe. Light from any object beyond this distance has simply not had enough time to reach us, given the age of the universe and the expansion history. The universe is 13.8 billion years old, but due to the expansion of space, the most distant objects we see are now far further away than 13.8 billion light years. Space stretched during the photon's multi-billion-year journey, so by the time it arrives, the source has receded to a much greater distance. Over time, the particle horizon gradually expands outward as more time elapses for light from more distant regions to finally reach us. Galaxies that were just beyond our view last year might, in principle, become visible next year, though the expansion makes this a slow process. The observable universe is thus slowly growing, incorporating more and more of the cosmos into our field of view. In contrast, the cosmic event horizon works in a fundamentally different and more forbidding way. It currently sits at a distance of roughly 16 billion light-years from Earth. This boundary marks the ultimate limit of possible future communication and knowledge. Any galaxy or event beyond this horizon is forever cut off from our future. Light emitted from beyond the event horizon today will never ever reach us, not in a year, not in 1 trillion years, never. The expansion of the space between us and those distant regions is so rapid that it exceeds the speed of light. The metric gap grows faster than light can possibly hope to traverse it. Even more unsettlingly, due to the acceleration of expansion, the cosmic event horizon is actually shrinking inward over time. More and more galaxies cross this horizon every moment, passing from the realm of potential future contact into permanent isolation. A galaxy that is visible to us today might cross the event horizon tomorrow. Its now will become forever inaccessible to us. Once a galaxy crosses, we can still see the light it emitted in the past. Those photons are already on their way to us. But we will never see what that galaxy looks like in the present. Its current state is eternally hidden from our view. This creates a deeply strange and poignant situation for cosmologists. We can observe galaxies up to 46 billion light-years away, but we see them via ancient light they emitted billions of years ago. Many of those same galaxies, if we could calculate their current distance, already lie beyond the 16 billion light-year event horizon. We see their history, a frozen image from their youth, but their present and their future are completely inaccessible. The image we observe will only get older and fainter, a fading portrait of a past that can never be updated. It is dark energy that drives this inexorable separation. Its accelerating push shrinks the event horizon inward while simultaneously pushing the distant galaxies themselves outward. These two walls are, in a sense, converging on our present from the future and the past. Eventually, trillions of years from now, only the gravitationally bound galaxies of our local group will remain inside our event horizon. Everything else will have vanished beyond it, making the observable universe a much smaller, lonelier place. Think about the profound implications this has for communication and knowledge. If an advanced alien civilization exists in a galaxy that is now 20 billion light-years away, contact is fundamentally impossible. Any signal we transmit, even at the speed of light, will never arrive. The space between us expands faster than the signal can propagate. They are, for all practical purposes, inhabitants of a separate universe forever beyond our reach. If they are sending out messages at this very moment, those messages will also never reach us. We are causally disconnected, isolated islands in an ever-widening ocean, forever unable to bridge the growing gap. The particle horizon defines what we can see of the past. The cosmic event horizon dictates what we can ever know of the future. Between them lies the entirety of our current, dynamic, observable universe. But as both horizons move, one slowly expanding, the other inexorably contracting, the cosmos we can perceive is constantly changing. Regions of the universe are forever fading from view, while others are slowly coming into sight for the first time. The universe we observe today is fundamentally different from the one our descendants will observe trillions of years from now. Two walls, one expanding with the past, one contracting with the future, together hide the vast majority of reality from our view. Watch a distant galaxy over billions of years through a hypothetical perfect telescope. The first thing you would notice is that its light is steadily growing redder. The wavelengths of the photons are being stretched by the expansion of the space through which they travel, a phenomenon known as cosmological redshift. Simultaneously, the galaxy would appear to grow dimmer, not just because it's farther away, but because fewer of its photons arrive per second. The expansion of space stretches the wavelength of light, reducing the energy of each individual photon. It also spreads the photons out over a larger area, reducing the number that hit our detectors. Eventually, the combined effect redshifts the light so far that it is shifted from the visible spectrum through the infrared and into the radio wavelengths. With sufficient time, even the radio waves are stretched into undetectably long wavelengths, and the photon flux becomes so sparse it is indistinguishable from noise. The galaxy fades from view entirely, not because it has ceased to exist or stopped shining, but because its light has been stretched into oblivion. This fate awaits every galaxy not gravitationally bound to our local group. Dark energy's accelerating expansion drives them away faster and faster. The light a galaxy emits today will be stretched more than the light it emitted yesterday, and tomorrow's light will be stretched even more severely. The redshift does not just increase linearly. It grows exponentially over cosmic time due to the Imagine a galaxy that emits 1 billion photons per second in our direction. If the scale of the universe doubles by the time that light arrives, those 1 billion photons are now spread over a sphere with 4 times the surface area. The number of photons hitting our telescope per square meter per second drops by a factor of 4. If the universe doubles again, the rate drops by another factor of 4, and so on. The galaxy dims with a rapidity that is breathtaking on a cosmic timescale. A galaxy that is a prominent feature in our sky today might become undetectable to any conceivable instrument within a few tens of billions of years. Its light still travels through the universe, but it is spread so thin and stretched so long that it is forever lost to observation. Many galaxies have already crossed this point of no return for current detection, and many more have crossed the ultimate threshold, the cosmic event horizon. For these galaxies, light they emit today will never reach us, because the space between us expands faster than light speed. However, we can still see their past. The photons they emitted billions of years ago when they were closer are still en route and arriving at our telescopes now. We observe a historical image, a snapshot of their ancient past, not their current state. Over time, even these historical images will fade and vanish. The ancient light will continue to redshift, first moving out of the visible, then the infrared, and finally into undetectable radio waves. The galaxy will have completely vanished from our observational record. It still exists somewhere beyond the horizon, but we have no way to detect it, measure it, or interact with it. For all practical purposes, from our perspective, it has left our universe. Gravitationally bound structures are the sole refuge from this cosmic vanishing act. Our Milky Way galaxy and the Andromeda galaxy are moving toward each other, their mutual gravity overpowering the global expansion. The entire local group of galaxies, including about 54 galaxies, is bound together by gravity. Expansion acts on the vast scales between these bound clusters, but not within them. Therefore, the Milky Way, Andromeda, the Triangulum galaxy, and their satellite galaxies will remain visible to each other forever. They will form a single isolated island in an ever-emptying cosmos. Everything else, every other galaxy cluster, every quasar, every filament of the cosmic web will vanish from sight. In 1 trillion years, the night sky for any observers in the Milky Way will be nearly empty of external galaxies. They will see only the stars of their own galaxy, and the fuzzy patches of Andromeda, and a few dozen dwarf galaxies. There will be no deep field photographs revealing thousands of galaxies in a tiny patch of sky. The universe will appear small, isolated, and dark. Astronomers in that distant future might never discover the expansion of the universe or the Big Bang. They would have no evidence of distant galaxies receding, and the cosmic microwave background radiation will have redshifted into complete invisibility. Their observable universe would consist only of what is gravitationally bound to them. This realization means we live in a special and very brief cosmic era. It is a golden window when the universe is transparent, filled with light, and its vastness is still visible. Before this time, the universe was too hot, dense, and opaque to see far. After this time, it will be too expanded and empty, with most of its content having disappeared beyond observational reach. Right now, we possess the unique capability to see billions of galaxies and map the large-scale structure of the cosmos. This opportunity is fleeting on a cosmic timescale. Galaxies are vanishing from our view, one by one, as the walls of darkness close in. The universe we can observe is a temporary, brilliant, and dying spectacle. The cosmic microwave background radiation comes from every direction in the sky with near-perfect uniformity. No matter where you point a radio telescope, you measure a background temperature of 2.725 Kelvin. This temperature is the same in all directions to within 1 part in 100,000, an astonishing degree of isotropy. This seems intuitively normal until you consider the causal relationships between these distant regions. Take 2 points on opposite sides of the sky. They are now separated by about 93 billion light years. Light from one point has been traveling toward us for 13.8 billion years. Light from the opposite point has also been traveling for 13.8 billion years. This means the two source regions are now 93 billion light years apart from each other. Crucially, light from one region could never have reached the other in the entire history of the universe. They have always been beyond each other's particle horizons. They have never been in causal contact. They have never exchanged information, energy, or heat. How, then, did they manage to reach the exact same temperature? In thermodynamics, temperature equalizes through contact and energy exchange. Heat flows from a hotter region to a colder one until equilibrium is achieved. This process requires causal connection, a way for the regions to communicate and balance their energies. The fact that the CMB is uniform across causally disconnected regions is a major paradox known as the horizon problem. Before the theory of inflation, this was a deep and unresolved mystery for the standard Big Bang model. Some physicists resorted to the idea that the universe simply began in a state of perfect uniformity by sheer, inexplicable coincidence. This amounted to an impossibly fine-tuned initial condition, an unsatisfying ad hoc assumption. Cosmic inflation solves this problem with an elegant and powerful mechanism. Before the inflationary epoch, the entire observable universe was compressed into a region vastly smaller than a proton. At that tiny scale, every part of what would become our universe was in intimate thermal contact. Energy could flow freely and instantaneously, allowing the temperature to perfectly equalize across the entire region. Then, inflation occurred, a period of exponential expansion, doubling the size of the universe perhaps 100 times or more in a tiny fraction of a second. Regions that were once touching were suddenly ripped apart to distances that would exceed the speed of light travel time. They were separated faster than any signal, even light, could have connected them. However, they retained the uniform temperature they had established when they were in causal contact. Think of drawing two dots very close together on a deflated balloon. Then, inflate the balloon to the size of the Earth. The dots are now miles apart, but they still share the same color and ink properties because they were applied when the balloon was small. That is what inflation did. It stretched a tiny, uniform patch into our entire observable universe, preserving its homogeneity. The uniformity we observe is a fossil, a relic of that primordial unity before the great stretching. Inflation not only explains the overall uniformity, but also the specific pattern of the tiny variations. During inflation, quantum fluctuations in the inflattened field itself were inevitable due to the uncertainty principle. These minute, random fluctuations in energy density were also stretched from the quantum scale to astronomical sizes. Regions with a tiny excess of energy became slightly denser and hotter. Regions with a deficit became slightly less dense and cooler. These magnified quantum ripples became the seeds for all future structure, the galaxies, clusters, and voids we see today. Without inflation, there is no compelling explanation for the horizon problem. With inflation, the solution is natural and predicts the specific statistical properties of the CMB anisotropies. The observed pattern of the CMB's temperature variations matches the predictions of inflationary theory with remarkable precision. The uniformity of the CMB is therefore one of the strongest pillars of evidence supporting the inflationary paradigm. The universe looks the same everywhere because everything we see was once part of a single, unified, microscopic domain. We are connected to the most distant quasars, not by a continuous history of contact, but by a shared origin in an infinitesimal volume. That connection was severed by a period of hyper-expansion that set the stage for all of cosmic history. The echo of that moment of unity still surrounds us in the perfect thermal equilibrium of the primordial glow. If the process of cosmic inflation happened once, as it did in our cosmic patch, the laws of physics suggest it probably happened countless times. This profound conclusion emerges naturally from the combination of inflationary theory and quantum mechanics. Once an inflating field gets started in one region of the primordial cosmos, quantum fluctuations can trigger it to start in adjacent regions. Each of these regions then undergoes its own exponential expansion, inflating into a gigantic bubble universe. The process is self-replicating and potentially eternal. As long as there is space that is still inflating, new bubbles can form within it. We would live inside one such bubble. Our entire observable universe is the aftermath of one inflationary event that ended 13.8 billion years ago. Beyond our cosmic horizon, other bubbles likely exist, each with its own Big Bang and its own subsequent history. Critically, each bubble could have different physical properties. The fundamental constants, like the strength of gravity, the mass of electrons, or even the number of spatial dimensions, might differ from bubble to bubble. Our bubble happens to have the specific values that allow for the formation of atoms, stars, planets, and ultimately, life. Most other bubbles might be sterile, perhaps collapsing immediately after formation or expanding so rapidly that no structures can form. This is the multiverse hypothesis. While it sounds like the domain of science fiction, it is a direct and robust prediction of taking our best theories of the early universe at face value. The unflattened field that drove our inflation is a quantum field, and such fields are subject to random fluctuations. Wherever the field retains a high energy value, inflation continues. Wherever it decays, a hot Big Bang and a bubble universe like ours is born. Some regions of the meta-universe are likely still inflating at this very moment, giving birth to new bubbles even as you read this. Each of these bubbles would be causally isolated from all the others. The space between the bubbles is itself inflating, expanding at speeds that forever exceed the speed of light. This makes travel or communication between bubbles a physical impossibility. An observer in another bubble could never detect our bubble, and we could never detect theirs. We are part of a vast, perhaps infinite, cosmic archipelago where each island universe is forever alone in an unobservable sea of nothingness.